All right, so last section we're going to look at for the parametric and polar stuff is the last half of 9.2. And remember that when you graph a point in polar, the two values that they give you are the r value and the theta value. R, comma, theta. What we're going to do now is look at more than just graphing a point. We're going to graph a collection of points now. So what we're going to do now is we're going to sketch a whole graph. Right? And what I want to do first is sketch the graph r equals 2. The graph r equals 2 means you can pick any coordinate you want in this format as long as the radius value is 2. So could somebody give me basically any angle you want? We just always have to keep the radius as 2. What would be an angle? Yep? 45. That is a point that would satisfy this equation. This equation just says r has to equal 2. Doesn't care what theta is at all. So that point 245 would be right there. Can someone give me another point that would satisfy this equation? Yeah?
230 degrees.
230, okay. So pretty close to the other one, but that's fine. 230, so there's another one. How about another point? Yeah?
2 negative 200.
All right, so 2 negative 200. So now I'm going to go right to negative 200 brings me halfway around, plus a little bit more. All right, let's do one more. Yeah?
275.
275. So that's going to put you right about there. Okay, the point is, if you keep graphing every possible angle you can think of, what shape do you get? Well, Matt?
Circle.
Yeah, you're going to get a circle. So r equals a number is how we write an equation of a circle in polar. Just r equals 2 is specifically a circle with a radius of 2. Let's try to sketch this on the calculator. So this will be the first time we've done a polar graph. So you're going to go to mode, and now you're going to put it in polar. Okay, that's the third option over, the one after parametric. If you have anything in there, go ahead and just clear it. You can graph up to 6 different things in polar. We're just going to graph 1. We're going to put in 2. And now, if you have a circle that has a radius of 2, how far left, right, up, and down does it go from the origin? Yeah. 2. It's always 2. So when I check my window, I could set my window to be like -3 to 3 and -3 to 3. That's plenty of a little bit of extra space for my sketch. Now, the thing that's similar to what we did with parametric are these 3 things. Theta is a parameter. You guys were giving me different values for the parameter right here. You gave me 45, 30, -200, 75. If we're doing this in radians, or let's say degrees, what do you think your parameter would have to start at and finish at for you to get a whole circle? Because right here, you only got 4 points on the circle. You didn't really get the whole circle. Yeah?
Would it start and end at the same point?
It would start and end at the same point. So what could you start at for an angle? Yeah?
0.
Could start at 0. And where could you end? Yep.
360.
360. And that would plot every single point around the circle. You have to go 0 to 360. How many points you plot is controlled by the step. If I was going 0 to 360, I would go by 2s. That'll plot 181 points. That's plenty to draw a circle. In radians, we don't go 0 to 360. We go 0 to 2 pi. Okay? Now, if you want to go 0 to 6.28, I would not go by 2s. you get 0, 2, 4, 6. You get 4 points to draw a circle. It's going to look like part of a diamond. It's not going to be good. 0.1 is a decent step to go by. Whenever you go by 0.1, you're getting 10 points per integer. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and the last one. You're going to the integer 6, so that's going to give you 60 points. Plus, you're going to get 0.2, 6.1, and 6.2 in there. So you're going to get about 62, maybe 63 points if you include the first one. That's plenty. So let's hit sketch, or hit graph. And how come it doesn't look like a circle? Yeah?
Because of how small you did your step. Like you did it 0.1 if you did it 0.2 and it did more like a circle.
So I don't mean like the jaggedness of it. I think that's about as smooth of a curve as you're going to get. But to me, that doesn't look like a circle. It looks like an oval. That's my question. Yeah?
5.
Yeah, we don't have the right window. Think about what you're doing. Your window is wider than it is tall. And look at how many units of space you crammed into each of those dimensions. You put 1, 2, 3, 4 units on the width, and you put 1, 2, 3 units. Oh, no. 1, 2. I should fix my tick marks. They're probably not going by ones. That can't be right. X scale, Y scale. Oh, did I just count wrong there? 1, 2, 3. Oh yeah, it's 3. Sorry. 1, 2, 3. So you've got 3 units on the width and 3 units on the height, but there's more room on the width for the 3 units, so it spreads them out more. That's why your picture is distorted. If you want to make it look proportional, you need a zoom 5. And now it looks proportional. Now, if you set your t-step higher, like 0.5, is that going to give you more points or less points on the graph? Yep.
Less points.
Less points. Gives you a lot less points, and I can now tell that is no longer circular. It looks more like an octagon or something. All right, you didn't plot enough points. Right. So that's the graph of r equals 2. Let's switch it and try theta equals 2. This is the difference, like if we were doing function notation of like y equals 5, x equals 5. One's a horizontal line, one's a vertical line. Well, we're switching it up with polar now. Instead of the first number equals something, let's try the second number equals something. So now, the radius can be any number you want. Please limit it to 4, because that's how many rings I have. But technically, the radius can be anything you want. But the angle has to be 2. Now, when I'm graphing, I like to have it in degrees. It makes it a little easier for me to figure out. So if I take 2, multiply by 180, divide by pi, that's accurate enough. That's about 114 degrees. And I mean, I'm not getting out a protractor to do this, so I'm just estimating. I'm going to go a little after 90, basically. All right, so that's the angle, a little more than 90. So could somebody give me a radius that has a theta value of 2? Yep.
2 and 114 minus 9.
Yeah, and I'll just leave it as 2 because it's in radians. So 2 for the radius, 2 for the angle. That's right 2, and then go around a little more than 90. Okay, there's 1. Can someone give me another point? Just make sure theta is always 2. You can let r be anything you want, but please fit it on the graph. Yep.
3.
3, comma what?
2.
2. So that would be 1, 2, 3, 114 degrees. I'm not getting a circle. What's another point? Yeah?
-4, 2.
-4, 2. So left 4, and then go a little bit more than 90 degrees. Maybe that's not perfect, but close enough. Does anyone see what kind of shape we're going to get here? Yep.
We're going to get a straight line.
Yep. We're getting a straight line through the origin. I'll try to fix it. Close enough. So when you let theta equal a number, you get a straight line through the origin. Now we could talk about lines that don't go through the origin and have a certain slope and intercept. We're not going to get into that. That's all we're going to talk about with lines. Okay, questions on that? You can't graph this on the calculator. The circle one, obviously you can. We did. The reason you can't graph the other one is because in polar, the calculator always sets it up as r equals. You can't change it to theta equals. That'd be like in function notation, changing it to x equals. Well, you can. It's always y equals. You can't do anything about that. Okay, so you can't graph the second one on the calculator. All right, let's take a look at this graph. Okay, we're not going to make a table. We're just going to type this in and see what it looks like. And it's 3 plus 3 sine theta. What I do want to do, though, is think about this value and how it can change, because I want to have an idea of my window. So if you want to figure out what r is going to be, break down the formula that's giving your r into smaller pieces. Start by looking at just this piece, sine theta. What's the biggest value that sine would ever be? No matter what you plug in for this angle, you'll never get a value in that box that's bigger than 1. Ashley?
1.
Yeah, you'll never get a value bigger than 1, and you'll never get a value smaller than what? Yep.
2.
The sine function, actually, it does go below the x-axis.
So -1.
-1. So the values in this box are going to range between -1 and 1. So use that information to figure out what r is going to range between. If this box came out to 1, what's 1 times 3?
3.
3 plus 3?
6.
6. You will never get a radius bigger than 6 in this problem. Now, let's see what happens if what came out in this box was a -1. What is -1 times 3? Yeah?
-3.
And what's -3 or 3 plus -3?
0.
0. So the radius in this problem will be 0 at one point. What does that mean if the radius is 0? Where would the point be? Yeah,
Origin.
the origin. So this graph will go through the origin. All right, let's graph it and see what it looks like. 3 plus 3 sine theta. Let's check our window. Anytime you're dealing with a trig function, generally you do have to go 0 to 2 pi to get a full picture. But they tell you that in this case as well. Okay. So 0 to 2 pi. We know that we could be up to 6 units away from the origin. That's a radius of 6 at the most. We don't know 6 units which way, up, down, left, or right. So let's set everything bigger than that. Let's go like -8 to 8, and let's do -8 to 8. So that gives us 6 units all the way around the origin. So we should be guaranteed it doesn't go off the screen. Okay, kind of what it looks like, but I gotta fix something. What do I have to fix here? I left it like this from the last time. Yep.
Your theta step.
Yeah, my theta step has to be smaller. increments of 0.5 are too big of increments. Think of it as like stairs that are too far apart. Right? We don't want that. What would be a better theta step than 0.5? Yep.
0.1.
Okay, let's do 0.1. And that is what it looks like. Now that's kind of a distorted picture. Let's do zoom 5, and you'll see it a little more proportional. And that is what the sketch looks like. Anyone have an idea of what that kind of looks like?
Can you repeat the question?
Just an idea of what you think that looks like. Yeah.
A heart.
It kind of looks like a heart. I mean, if I brought this in a little more, maybe, then I could kind of make it look like a heart. But it kind of has that pattern of a heart to it, and that's why the shape is called a cardioid.
I was going to say an upside down apple.
Oh, an upside down apple? That'd be an apple. So this is a cardioid. Cardioids can be bigger or smaller. It all depends how you change this number. But those two numbers have to be the same for it to be a cardioid. Ours was 3 plus 3 sine theta. Watch what happens if you do 2 plus 2 sine theta. It's going to be a little bit smaller. But notice it still goes through the origin. So that's actually a point where the two cardioids meet. But it did make it a little smaller. Okay? Now, I said that you can do it with sine, and that's what we did it with, but you can also do it with cosine. And what happens if you change it to cosine? Well, let me show you. Anyone have a guess what's going to change? Yeah?
It's going to be flipped around so the point that they touch is going to be on the top.
Yeah, so what cosine does is it does rotate it. Right? If you do 3 plus 3 cosine, which is clear the other one, your cardioid is now kind of on its side. And you can make the cardioid face any way you want. You could do face left, face right, up, down, you can flip it. But the idea is anytime you have a formula that fits this pattern, or this pattern, it's a cardioid. Now you can't let A equal 0, because if A is 0, then you wipe out your whole formula. Then you don't have any. Now, watch what happens if you make the numbers different. This is not a cardioid. Let's do 3 plus 6 cosine theta. So what happened there is it doesn't really have a point where it indents. It actually comes in and loops on itself and goes back out. Okay, not a cardioid, according to the definition our book uses. All right. And the further apart you make these numbers, the more of a loop you get. Now we're getting an even bigger loop. Now if you switch it, and let's say instead of the second number bigger, make the first number bigger. Let's make that a 5, make that a 3. This is not a cardioid either. And it's like it starts to smooth out that indent of the heart. It almost starts to flatten it out a little bit. So it's, again, a little bit different shape, but not cardioid. Your parameter only has to go from 0 to 2 pi. What would happen if I try to draw a cardioid and I set it to 4 pi? What's the calculator going to do? Yep.
Would it overlap it?
Yeah, it's going to trace over it. So I'll just use the picture that I have in there. Let's set this to 4 pi. And watch it carefully because the calculator rounds. And depending on where it rounds, controls which pixel it lights up on the screen. It may round slightly different the second time around. What does that mean? It might make it look a little bolder. So let's watch it. There's the first time. Yep. And I could see it going around the second time. It didn't quite do it in the same spot. Theoretically, it should, but it doesn't because of rounding. All right. So if you see it getting bold, you're going around more times than you need to. Okay. Questions on that? Okay. So let's take a look at how we can convert not a polar point to a rectangular point, but a whole polar equation to a rectangular equation. Let's just remember what we did yesterday. When we wanted to convert from polar to rectangular, r theta to xy. Does anybody remember what was the formula for x? It's x equals and then something. Yeah?
R cosine theta.
Yeah? And what about the formula for y? What was that one? Yeah?
R sine theta.
Okay, so we can use those two. So these two formulas give you a connection between polar and rectangular. Polar and rectangular. And then we had two other ones. What was the formula we used to find the radius when you were converting to polar? Yep.
It was inverse tangent y under x.
Okay, so that's for the angle, inverse tangent y over x. How about the formula we used yesterday to find the radius? Yeah? Yeah, it was the Pythagorean theorem. So these are the four formulas that we've learned that connect a polar and a rectangular concept. We're going to use these formulas to change an equation into rectangular. And the equation that we're going to do is this. 3 plus 3 sine theta. We just talked about this. What shape is this? 3 plus 3 sine. Yep.
Cardioid.
It's a cardioid. So what we're going to do is convert this into rectangular. That means when you're done, no r's, no thetas, no sines, no cosines. All you're allowed to have is x's and y's. Let's start with this. Sine theta. If I see a trig function and I know I'm trying to convert to rectangular, I try to get rid of that one first. We scroll back up. Which formula here do you think we're going to be able to use? Let's just number them so it's easier to talk about them. We're going to replace sine theta. So what formula do you think we're going to look at? Chris?
Number 4.
Well, there's no sine theta in that formula though.
Oh, wait.
So I'm not sure where we would pull sine theta from there.
I meant y.
Yeah.
It's 2.
Formula 2. So using formula 2, what does sine theta equal? You have to rearrange it a little bit. But if you rearrange formula 2 and get sine by itself, what would be on the other side? Yeah?
Y over r.
Yeah. Sine is defined as y over r. That's really like saying sine is opposite over hypotenuse. If you draw a triangle and you put theta, you know, actually, how do we normally do it? Like this. Draw a triangle, put theta, this is y, this is r. Y is the height, r is the radius, and the sine is opposite over hypotenuse, y over r. So that's the substitution we're going to start with. And now change sine to y over r. Okay, so y over r just took the place of sine. So that's good. Now, what I don't like that just happened is now we have a fraction. What could I multiply everything by so I don't have r in the denominator? Yeah.
Multiply it all by r.
Yeah. If you multiply everything by r, that's going to clear your fractions. Times r, times r, times r. Casey, what's r times r? R squared. And Matt, 3 times r?
3r.
3r. And Abigail, 3 times y divided by r times r. 3y. Okay. So now, there's only 2 things here we have to get rid of. Can someone tell me one thing that we can't leave in this equation if we're trying to get it in rectangular? Yeah?
The r squared.
We can't leave the r squared here. Do we have a formula for what r squared is equal to? Yeah?
Third one.
Yep. And what is it? What is r squared equal?
X squared plus y squared.
Yes. So we can change r squared to x squared plus y squared. And if you have r squared and you want to get r, well, what do you do with r squared to turn it into r? Yeah.
Take the square root.
Take the square root. So take what we just wrote down, this is r squared, take the square root of it. That's all you can do. You cannot say that that is x plus y. That is not a rule that you can use at all. And that's it. That's the equation of a cardioid in rectangular. I'm not saying you could type that in on a graphing calculator. You couldn't, because think about with a graphing calculator, it can only graph things that pass the vertical line test. Well, cardioids definitely do not. They fail. So maybe if you were clever, you could do it like we've done circles, do the bottom and the top half separate. But there's no way you're going to type that in all at once. Yeah.
What did you do with the 3r?
The 3. Oh, I just forgot the 3. I'm sorry.
Oh.
Thank you. So the 3 is still there. So r squared is x squared plus y squared. The 3 just gets copied down. This is what Jack said. It's the square root of r. And then the 3y gets copied down. Yes, it is important to keep that 3. Okay. Any question on that? All right, so that's converting a polar equation to a rectangular equation. Let's look at converting a polar equation now to a parametric equation. Okay, so this is polar to parametric. So when we want to do something in parametric, how many equations do you need to type in to get a picture? Yeah.
2.
Yeah, you need 2. One for the x values, one for the y values. Now, imagine you had a sketch, and it looks something like this. All right, doesn't matter. There's your sketch. And let's say we had a formula for this that was r equals some function of theta. I don't know what the formula is. Could be 3 plus 3 sine theta. Maybe it's a cardioid shape. Maybe it's whatever it is. There's a formula that would give you this picture. Forget about the entire picture. Focus on one single point. If we want to convert this point into parametric, we need to know 2 things about it. The x value and the y value. Whoops. Y value. Are you laughing at me? So we got x and y. think about what you would know in polar about this point. You would know two things about it. You would know that. That's your radius to the point. That's r. The other thing you would know is how many degrees you rotated to get up exactly to that point. You would know theta. Make a triangle. This side is x, this side is y. If I just wanted the coordinates of that one single point, forget about anything else here, just focus on that one point. The x formula, we just wrote it down, is r, somewhere, r cosine theta. And the y formula is r sine theta. Now, for any point on this curve, no matter where you put it, you could measure the r value. So my question is the r value the same for every one of these points? Yeah?
No.
No. They all have a different r value. Right? That one is that one is that one's even longer over here. They all have a different radius, which means they all have a different x and y. They still have an angle. Okay? They're all going to have some angle theta that you had to rotate, but they're all going to go out different amounts. So this value right here is not a fixed value. It changes. You have to be able to calculate it. While in polar, that's exactly what the formula does for you. The formula is r equals a function. The formula they give you will tell you how big the radius is. So if you take and plug this in, what you get is f of theta cosine theta, and y equals f of theta sine theta. You get two different equations, and here is the calculation for the radius. It's the formula that they give you. Let me write that down. So this is formula you are given. The formula you're given times the sine will give you the y value, and the formula that you're given times the cosine will give you the x value. If r was fixed, I wouldn't have to give you a formula here. I could just say, oh, r is always 3. We're doing a circle. But it's not a circle. So you use the formula to find the radius, and then multiply that by the cosine for the x and by the sine for the y. Now, the only thing you're going to see in these two formulas, when we do it in parametric, we don't use theta as the variable. What letter do we use? Yeah?
T, right?
T. So in parametric, theta will become T. So instead of when we graph this on the calculator, we're going to have to use a T. You can't use theta. But that's how you convert polar to parametric. Take the polar equation times the cosine, and the polar equation times the sine. Let's try it. Here's your polar equation. 7 sine 2 theta. So now the polar equation itself has a sine in it. That's fine. We still have to multiply it by what I said right here. Whatever they give you times the cosine, and whatever they give you times the sine. So, what did they give me for the formula? For the radius. Well, Matt?
7.
What's the whole thing?
7 sine 20. I mean, 7 sine to
7 sine 2 theta. So that's going to go in each of these spots. That number that you get when you do that calculation from that red expression is this distance right here. It's giving you that. Or for a different point, it'll give you that. Or it'll give you that. It'll give you different values depending on what you plug in. So that's giving you the radius. And what do we multiply the radius by to get the x part of this? Yep.
As of theta.
So this is our function of theta. And then what do we multiply? Because what you have right now, if you want to think of it as a triangle, you've got this side. That's your radius. But I don't want that side. I want this side. And there's your angle right there. So what do you multiply the hypotenuse by to get the base in a triangle? Yep.
Probably the cosine.
The cosine. Multiply it by the cosine. And technically, what letter should I be using here? I told you this earlier.
T.
I should be using T. Let's make that a T. Okay. And now, this is your radius again. What would you multiply your radius by, or what would you multiply the hypotenuse by to get the height of a triangle? Yep.
The sine of t.
You multiply by the sine. Hypotenuse times cosine always gives you the base. Hypotenuse times sine always gives you the height. And there is how you convert parametric or polar to parametric. Let's graph it. Okay, I'm in polar, so I'm going to do that one first. 7 sine 2 theta. I'm going to set my window. First of all, I just want to go 0 to 2 pi. I don't want it to trace over itself. And let's hit graph. There you go. That's the picture of 7 sine 2 theta. So let me put that here, and I'll put how I did it right next to it. So this was polar. Now let's switch over to parametric and type in what we found, and it should look exactly the same. So let's go to parametric. Put in 7 sine 2t cosine t. 7 sine 2t cosine t. Put in 7 sine 2t sine t. Check your parameter. Yeah, looks fine. Hit graph. It's drawing a little slower. Maybe that's because parametric isn't as efficient of a way to do this graph, but you get the same graph. Got exactly the same picture. So there's the picture, and here's what I typed in to get it. Polar, parametric. Which one do you think is simpler for drawing this shape? Yeah.
Polar.
I would say polar. You could type in less stuff. This kind of shape, polar is better. Some shapes, parametric might be better. Depends on what you're trying to sketch. Now, just focus back on the polar one. Let me make that a little bigger. This 7 is in the diagram somewhere. Does anyone have an idea what the 7 would do? It controls something in the picture. It does. It controls the size of the petals. Draw something 7 units long. So 1, 2, 3, 4, 5, 6, 7. I think that's about 7. Now, take that line segment I just drew. I'm trying to rotate it. I'm trying to put it the best I can. Now, maybe I can just move the picture. It needs to be rotated more. That's as good as I can do. The 7 is the length of the petal. That's what the 7 is. Now the width changes a little bit as well. I don't know exactly what the width of the petal is, but I can tell you that the length of the petal is exactly the number in front, 7. The 7 controls the length of the petal. What do you think the 2 controls? Something other than the size of the petal. Yep.
Number of petals.
Mm-hmm. Controls the number of petals. So based on that, if I were to put in, let's say, a 4. Bless you. How many petals do you think I would get if I changed the 2 to a 4? Yep.
8.
All right, let's try it. Getting a little rough on those edges. Probably should change the theta step a little bit. But yeah, you got 8. What if I plug in 3? How many petals do you think I'm going to get? Yeah?
6.
I can see why you would think 6, because so far it's always been double the number. And if you put in an even number, you do get double the number of petals. If you put in an odd number, you get exactly that number. And the first one we did was called a 4-petaled rose. That's the name of that graph. 4-petaled rose. Each petal has a length of whatever the absolute value of the number in front is. And if you're wondering what would happen if you make the number in front a negative, try it. See what happens. We've put negatives in front of graphs before, so you should know what a negative would do. But the absolute value of the number in front is the length of the petal. Again, the width, I don't know. I'm not exactly sure. You could calculate the width of the petal somehow. Just not sure what that is off the top of my head. You'd somehow have to find the 2 coordinates of the widest point of the petal and then use the distance formula between them. And maybe it has a connection with the 7. I don't know. They'll probably do it for several values and see if there's a pattern. And the last shape we're going to look at is a spiral. So a spiral is basically a radius that grows as you rotate. The spiral of Archimedes has a radius that is always equal to the angle. So if you do this in degrees, think about what your parameter has to be, 0 to 360. Well, if you draw a spiral in degrees and let theta go from 0 to 360, then you better set your window to be close to 400 units wide, or you're not going to see the whole spiral. So let's try it in radians, and we'll do a few different windows. Let's try 0 to 2 pi. Okay, when I sketch 0 to 2 pi, how many revolutions of the spiral do you think I'm going to get? 0 to 2 pi, yep. You're going to get 1. And since the spiral of Archimedes has the radius equal to the angle, what's the biggest radius that I'm going to get if I go 0 to 2 pi? radius is always equal to the angle, and this is what your angle is starting at, and this is what your angle is stopping at. So what's the biggest radius you'll get? Yeah?
2 pi.
2 pi. Now, it's a spiral. So technically you don't need to go 2 pi on every axis. There is only one part of the picture where the spiral is going to be the furthest away from the origin. If you want to be safe, you can just set your window negative 2 pi to 2 pi every direction. And that's kind of overkill, but it'll work. So let's do negative 2 pi to 2 pi, negative 2 pi to 2 pi. I do need to set my parameters 0, what do they want? 0 to 2 pi on the first one. Okay, that's already set. Hit graph, and there's your spiral. Okay, exactly 1 revolution. And the only place that you really needed to go all the way to the maximum arm of the spiral was at the x-max. You didn't really need it at the y-max, the x-min, or the y-min. Just the x-max. Now, what if I do 0 to 4 pi? How's that graph going to look different than this one? Oh, Bailey, what's going to be the difference when I do 0 to 4 pi?
It's going to look more of a spiral.
Is it going to trace over itself? No. This graph never traces back over itself, like a cardioid or a circle or something like that would. This just spirals out further and further. So if we go 0 to 4 pi, and I hit graph, is that a good window for 2 revolutions of the spiral? No. I should have set my window bigger because now the spiral is getting bigger. It's going to be the biggest when you hit the positive x-axis. But if you want to be safe, do negative 4 pi to 4 pi on everything. And that's more than enough to see exactly 2 revolutions of the spiral. There you go. So there's 2. And if you did 0 to 8 pi, you would get double the revolutions we just got here. You get 4 revolutions. But again, you got to keep zooming out so you can see the whole spiral. Any question on how you do 0 to 8 pi? All right, so that's graphing spirals. And that's pretty much all we cover about parametric and polar. There's a lot more stuff you can talk about, but this just kind of gives you like a quick idea of some of the kinds of shapes you can draw. Shapes we definitely haven't seen up until this point in the year. All right, so those are the questions for tonight. So 19 to 21, 24, 30, 31, 33, 37 to 41 odd, and 43 to 47 odd. I think it's about the same amount of questions as last night. It's just broken up a lot. Actually, it might be less questions than last night. We'll take a look at that tomorrow. And then tomorrow we're going to do section 9.4. One thing I want to mention is 9.4 is from a different book. So in case I forget to mention it, if you borrowed a book from me at the beginning of the year, and that's what you've been using each night for the homework, don't use it for tomorrow. Look at the PDF on Schoology.